All right.
Great. So thank you for the invitation to this workshop. And today I will talk about real systems, so the computing center where I work. So it's the N2P3 Computing Center in Lyon, France, and it's a center dedicated to the processing of the data produced by the largest experiment in energy physics and astroparticle physics. So the LHC, the next telescopes in Chile, the Virgo and LIGO experience for gravitational waves. And so to serve all these experiments, we have almost 35,000 virtual cores and a lot of storage, a lot of data to store. And we provide resources for almost 80 scientific collaborations, which represents 2,500 different users. And the slight difference with regard to all the workloads we discussed during our presentation and what is usually presented as this workshop is that our workload is a high throughput computing workload. So we still have some rectangles to schedule, but it's like playing Tetris with only the long bars. So it's almost only one core jobs and running for a long time for some of them. But there is almost no parallelism and for sure no multi-node jobs. And so recently we split our system in two parts. So all the jobs coming from the grid, which are managed upstream by robots that smooth the load for the different computing centers they're trying to deal with, are now handled by HT Condor, but we still have what we call the local jobs submitted by actual humans, managed by traditional batch systems, so univalued engine. And so the motivation for this work is that univalued engine implements the fair share scaling algorithm. And in opposition to what conservative backfilling or easy can do, you have no estimation of when your job will start when you submit it. And so the user has no way to know when they will have the results, even if they know the runtime of the jobs. And so if we look at the distribution of the job wait time for a fair amount of time, so for 23 weeks, digging in the log from 2 years ago, we saw that we have almost 6 million jobs, and it's pretty distributed in four parts. So 1/3 of the jobs are starting almost immediately. Another third is starting in less than 30 minutes, which is quite fair because we ask our users to submit jobs that are running for at least 1 hour. And then we have the urban section, which represents 1/3, where jobs can start between half an hour and 9 hours. And you can see you have a log normal distribution because you have a log scale on the x-axis. And so users may wait only a little or a lot of time. And then you have a long tail with almost 10% of jobs that wait for more than 9 hours. And so showing that, three questions we ask ourselves, was, can we explain why a job waits more than another? And can we use some knowledge extracted from the log to train some machine learning algorithms? And thanks to this learning algorithm, can we get a good estimation of the job wait time especially for the last two zones, the orange one and the red one? So to answer this question, the outline of my talk will be as following. So we start by analyzing the 23 weeks of logs that we had and try to identify some classical and intuitive causes that job system administrators can derive for this job wait time. And then we try to train some algorithms, and we had to select which kind of machine learning algorithms to use, and then apply them to our workload and see what we can get from there. So first set of intuitive causes. So it was addressed by Draw in this talk. So who is submitting the job. So user, the human in the loop is important, and it has an impact also on the with the fair share algorithm on all users can access and how many resources a user or group can access. Because at our center, every group express some pledges for the year, so they want that number of hours or that number of HS06, which is a word unit used by energy physicists, and they get. So we aggregate all these pledges and define the total computing power needed by all the experiments. And if we have enough power, we just split them among the group, or we buy some new machines to be able to serve everyone. And so each group in the end gets a proportional share of this of the resources, and this share defines the consumption objective for the algorithm, and the fair share algorithm derives the priority for the jobs based on that. So what we can learn from that is that small groups with small pledges will have access to less resources, so they are likely to wait more if they submit a lot of jobs. And because of the algorithm, if you overconsume your share for a short period of time, you have to pay it for after. So if you overconsume, then you have a lower priority. So when you submit jobs and other groups with higher priority are also in the system, you will have to wait. And final cause also that we saw is that our system, we have operators that monitor the load and the access to the resources, and they can manually block some users if you are not respecting the policy of the center, or you are making the storage system crash, you are blocked and your jobs are suspended for a long time. So we saw that in the log that some people are blocked for months. And when you look at the log, you see a job submitted in March and actually started in June, because of the user was just blocked for a long period of time. So you have to clean the log also for that. Second cause of wait time is the request made by the job. So this is something that is classical in HPC. If you ask for more time, you are less able to be backfilled. So you will be waiting more. The same applies to memory, which is data we do not have in the standard workload format, I think, or not always. And if you add more cores, you have a big job, so it's harder to schedule and so on and so on. And what we saw also in the center is that if you want to access to special resources, so a particular storage subsystem or something like that, or you need a license for your scientific code, you may be submitted to quotas. And depending if the quotas are reached at your user level, group level, or at the global scale, your job will have to wait also. And we saw some weird situation like this one, where a user has submitted 2,000 jobs in less than a minute, and his group has a quota of maximum of 90 jobs running at the same time. And when you plot the Gantt chart of the execution of these jobs, you will see that all the jobs pass, but they take 6 days to execute 2,000 jobs. And if this quota was increased to 1,000 jobs, which is it has been increased to 1,000 jobs a few months later, all the jobs will have been executed in less than 2 hours. So quotas are important, and this is an information we do not have usually in the log, but which may be important for the scaling decision also. This one will be quick because we saw these patterns already in our presentation. So the business days and week and night pattern with low load and so on. But also what can influence the wait time of a job is the current status of the system. So how many jobs are currently stacking in queues, and also the number of job already consuming resources, which is not the same metric, but both are important. And we saw some particular behavior when we see a correlation between the wait time and the state of the system. So this is something that we want to take into account in our learning techniques. So based on that, we try to select a set of features depending on the information we got in the logs and the analysis we made of the workload. And we try to solve two problems. So the first one, and try to apply machine learning techniques to this classical problem. So the first one is a regression problem. So we try to estimate the exact wait time that a job will experience when it's submitted, which is quite foolish to do because it's likely to be very imprecise. And moreover, users may not really want to have that degree of precision. You don't want to know that your job will start in 8 minutes and 43 seconds. But what you are more interested in is that will my job start in less than half an hour, or in 8 hours, or in more than 1 day? So this is why we tried also to solve a classification problem. So we define different time range based on the distribution of the wait times that we saw on the log, and try to divide the orange and red zones in more tight range, and try to see if we can get that kind of estimation back to the users and inform them that they are likely to wait for that amount of time. And then to decide which algorithm to use, we decided to study the learning and prediction times because we want them to be fast, because in the end we want to use them in production in the system. And to estimate the quality of the estimation, we studied the distribution of the error, and for the classification, we relied on confusion matrices. So, so what did we use for as algorithms? So we didn't develop new algorithms. We just rely on classic off-the-shelf implementation provided by scikit-learn, and we favor fast algorithms. So for the regression problem, we just tried a simple linear regression, simple decision tree regressor, and some ensemble methods that use the decision tree as a weak learner and try to aggregate the information given by these weak learners to provide with to end up with a better estimation. And for the classification problem, we have also the same approach. You just replace regressor by classifier with the same kind of algorithm, and the linear regression is replaced by an AIS-based classifier. And in addition to these two families of algorithms to solve our two problems, we also tried another approach that is in two steps. So first, we solve the regression problem. So we try to guesstimate the exact amount of time a job will wait, and then we fit it in one of the categories. So we first do the regression and then classify the results of the regression. Okay, so in terms of accuracy and comparison of the different algorithm we tried, so we can see that AdaBoost, so what we make vary there is the depth of the decision tree that is used as a learner, and we can see that all the algorithm improve when you go for deeper trees, but you may risk, if you go too deep, you may risk to do an overfitting of your data, so you have to cut a little bit before to be sure that you are not just overfitting your data. And we can see that AdaBoost is not as good as the bagging method and decision tree regressor. And if we split the accuracy of the different algorithms by grouping the jobs by the known wait times they experience in the log, we can see that it's slightly better for what we call the early starters, so the job starting in less than half an hour. And we also see a huge degradation for the jobs that wait actually in the system for more than 9 hours. But it's less important to have a big degradation for these jobs, because it means that you may predict you have a big error, but you had a big error, a big wait time at the beginning too. So if you are off by 9 hours for jobs that waited for half an hour, it's important. If you have a 9-hour error for jobs that waited for 2 days, it's less important. Always miss the okay, so more general results about the accuracy of the classification, the solution to the classification problems. So this table shows that the percentage of jobs that are predicted in the right time range. So if a job waited for in the system for less than half an hour, we predict that it will wait for less than half an hour too. And then we also consider that the percentage of jobs that are classified in one of the adjacent categories. So if we have a category between 30 minutes and 2 hours, we also consider less than 30 minutes and from 2 hours to 4 hours. So not perfect, but not so bad. And if we compare the different algorithms that we use, we can see that the DI classifiers are very close performance, because they almost all predict between 45 and 50% of the jobs in the right range, even the most naive one. And the performance for the combined, so if you combine correct and adjacent time range, they are almost the same for the advanced classifiers. And if we look at the extra options that we followed to first do a regression and then a classification, we see that it's really bad to predict jobs in the right category, in the right range. But if we use the adjacent ones, it becomes the best. So the one with a higher percentage of jobs predicted in the correct or adjacent category. So, which one is really the best predictor that we can decide to deploy on a producer system to help our users to know how much time their job will wait? So, to decide that, we have to look at the classification matrix, the confusion matrix, because as I said just before, if you look at the percentage of prediction in the correct category, the naive Bayes classifier is not so bad. But if you look at how it classifies a job, so on each line you have the measured wait time in the log, and on the column you have the predicted wait time. So you want to be you want to be good on the diagonal. And what we see for the naive Bayes classifier is that it's really good for the short job, because it's predict everything to run to start within half an hour. So you have a good score for the first category and extremely bad for all the others. And if you look at the other direct classifiers, they are slightly better. So they are able to predict a fair amount of jobs in the right category. So what is displayed in the right panel, so if you can read the numbers, just the color and the intensity of the red gives you a hint of the quality of the prediction. And the darker you are, the most jobs are close to the diagonal, so close to the prediction is close to what they really experience in the system. But we see a degradation as the job wait longer, because they all tend to predict jobs to start really soon after the simulation. If we look a bit closer to what is achieved by the combined approach of regression plus classification, we saw that the bad percentage of jobs in the right categories, because we are not able to predict jobs in that upper left corner, and it's just because we looked at the result for the panel just after, and we saw that a lot of jobs were predicted to wait for 39 minutes instead of less than 30 minutes. So instead of having a lot of jobs there, they are just right here. So not that bad. And if we look at the band, the diagonal band with the adjacent category, we have the results on the right, and it's almost always more than 50% of the jobs that are in these categories. So not that bad. So to conclude, so what we did in this work, we analyzed a lot of jobs, so 6 million of jobs were submitted for 33 weeks, and try to derive some intuitive codes that we use to extract features that can be used to train some algorithms and obtain some promising results for these two problems. And what we want to do next is to try to improve our prediction. And one thing we think will be promising is that to try to better take this early starting job into account, because there are a lot of them, and we have to put more weight in the learning on that category. We will also try to use some deep learning algorithms and not only machine learning algorithms. And on a more practical side, what we would like to do is to automate and transfer the analysis procedure we made to the team in charge of the user support at our center, and try to integrate that in user portals that can give information to the users about how much time they will wait when they submit a job. So I don't know how much time I have left.
3 minutes.
3 minutes. So okay, I have some bonus, because in the review I said, okay, what will happen if you apply your techniques to another workload? So we did try that. It's not included in the paper. It will be, I think, for the final version. So we selected the last entry of the parallel workload archive. So provided by Mehmet, the workload of Kit, which is really different because there are much less job, much less users, and much longer period of time, over 2 years. And I will be quick to present that. If we look at the confusion matrix, we apply the same techniques, but it does not lead to the same results. So if you look at the right panel there, it's much faint than this one that I just presented before. But there are some reasons for that. First, if we look at the utilization of the resource, on the left you have the resource utilization of our centers, so we're close to 1% all the time. So we have much more job waiting for resources because it's almost always full. We have a 93% of resource utilization on average. And on the workload from Kit, you have only 60%. So if you have less jobs, less occupation, you have more resource available when you are submitting jobs. And if we look at the distribution of the waiting time, we see that the part of job running in less than 10 seconds is much higher. And if we group with the job starting in less than 5 minutes, it's 3/3 of the workload. So waiting time is less important because users do not wait a lot on this system. And we also have an impact of backfilling, because if you this scheduling system is implementing backfilling, so if you submit a job and it's small, it will start earlier also. The submission patterns are also not the same. So there it is really clear. You have business days and everything else. So less categories, so you have to include that also in the learning. So change a little bit the features that are given to the training algorithms. And if we look at the different correlations, what we can see is that we have less information, because on our system, as we know the admin, we have access directly to the log. We have access, as Dalibor mentioned earlier, we have access to the shares, we have access to the quotas, and we have access to the queues and limitation, and all the information that usually you don't detail in the log because there are not of interest for many people outside your center. And so, but they are needed if you want to train your algorithm better. So that's it. So we think that our method can be applied, but you need to be careful of what you're doing, and you will not be able to apply it like that. You will have to review it, and And the good news is that we did a companion to the article, so we have one reference in the bibliography, and when the slide will be made available there, this is a link. So this is a 45-page document that describes all the scripts and all the analysis made to produce the data in the paper. And all the data are also available. So there is a table on Figshare that you can get and try also at home and try on all your system logs. And if you do so, let us know about the results. And if you have questions, of course, you can ask them. Okay, that's all for me.
Very nice. Gonzalo, we have
got a couple of questions if we have time.
We don't have much time, but go on.
Just super quick. So have you tried reapplying the same algorithm to simulate a system that is just like yours but larger?
So same
does
system
it still hold? So imagine a system like yours, but it's like much bigger than what it is right now. Would it still hold?
I don't know. We didn't try that, but this is something that we could do and try to reduce the pressure that we saw. Right now we are close to the full utilization of the cluster. So maybe if we give more slack, you will see some difference in the wait time, and this is something we could try. Yeah.
And the second part, just curiosity, the scheduler that your target system has, does it enforce FIFO within queues of the same user group?
I don't think so.
Okay, so it's just high throughput. If a job can be placed, you place it, and it doesn't matter if you arrive later than. Okay.
Yeah, as soon as you, in fact, it computes priority based on groups and on the global system, and once you have the priorities, first come first serve.
I see. And in that system, are jobs allowed to have like random resource shapes, or do you have some kind of instance types or like fixed resource size? It's like the job can request anything like a core or all the RAM of a node, or do you have like fixed sizes that jobs can request?
They have some you have some limits that are enforced by the queues. So you can ask for more than 3 gigabit of memory per job, something like that.
I see.
And then the user can ask whatever they want in terms of number of cores, but they don't. They just go for 1 or 8. Usually.
Okay, got it. Okay, thank you.
Except for maybe a dozen of users that do something else.
Cool. Thank you. To keep our timing good, please, the next speaker will be Abel, and the title of his talk is, oh my God, I got lost. HPC co-scheduler with reinforcement learning. Sorry for my confusion. The floor is yours, Abel.
Trying to share my screen here. Oops. I think the permissions of Can you see the screen?
No.
Yes. So yeah. Good.
It's good. Okay.
Okay.
Is it It's moving? Yes.
Yes.
Right?
Yeah.
Okay.
Great.
Okay. Thanks. Sorry for this. Yeah, my name is Abel Souza. I'm a research engineer at UME University. I recently graduated with my PhD last year during COVID. And today I'm going to present our paper, HPC co-scheduler with reinforcement learning. Experimental data are increasingly being processed on HPC systems and usually as scientific workflows. They support many scientific experiments where data come from different sensors and sources. such as real-time streaming. For example, in the figure, we have a direct secret graph that represents scientific workflows, and where the output from one stage in this application is used as the output of one stage is used as input for the coming stage. So, and these workflows are also represented by different stages. For example, each column in this DAG represents a processing phase or a stage in this scientific application. The computational tasks in this scientific workflow can be decomposed by multiple jobs, and each job will have varying resource needs, for example, such as number of processors. In this figure also, like parallel regions are expressed by multiple green nodes in this DAG, and use all the resource available for that job. Sequential regions, on the other hand, are represented by just single nodes, the red, orange, and black. And they only use, like, let's say you have 10 cores allocated to that job, they would be using only one, and the other 9 cores would be idling. Okay, and if we are going to take the most traditional architecture that is using HPC, is basically the use of space sharing. And jobs always go through a queue, a priority queue. They have to wait there when the user submit them. And the thing with space sharing is that it doesn't allow resource to be multiplex among different jobs. So in this figure, we have the upside down triangle, the green triangle, that could probably be using either resource, but it's not, because space sharing, the policy doesn't allow this job to be collocated there. Besides that, the common policy in HPC is to be very static. So it's very deterministic on the decisions that it takes. So it's actually it's not that anything bad or good. It's just that it's very deterministic. So it doesn't really allow probabilistic decisions to be taken. So okay, and then we have this reinforcement learning framework, and what is it, and how can we integrate this into HPC? So reinforcement learning is a mathematical framework so that it tries to optimize a reward or utility function by acting on the environment in question, in the use case that you are trying to model with this framework. So you basically have an agent, and it takes actions in this environment, and it then observes what the output of that action, and then it collects a reward, which basically tells if the action that the agent just took was good or bad, and it can also observe the state resulting of that action on the environment. Okay, if we were to integrate this into the HPC, into a HPC data center or resource manager, we would basically have the agent would be represented as the scheduler, the environment would be the cluster itself, the actions that would be making, would be could be resource allocation, for example, how many resources to give to a job, and the reward would be how fast or slow is job run in relation to a normalized behavior, like for example running a job in the cluster totally isolated, the most optimal way, a lot of free resource. This could be compared to a case where you run 2 jobs and you see how faster or slower these jobs are running. So this reward function can represent that. And the state of that that we could use could be key performance indicators like, for example, cluster utilization or queue waiting time. Okay, so then that's exactly what we are trying to do in this paper. We're doing in this paper where we present ASAX that we call the adaptive scheduling and extended architecture. Is a very fancy name, but so what we are basically doing is we have, instead of taking deterministic decision, co-scheduling decisions, we take probabilistic. So we basically take co-scheduled jobs and observe what was the output of collocating two jobs together, and this creates a probability distribution that represents to the scheduler if co-scheduling decisions will result in a good or bad thing. And I will explain later what good and bad means here. It basically takes into consideration the state of the cluster, because it evaluates those key performance indicators at runtime, and it also allows the users and operators to express the policy in a way that that can be analytically evaluated. So it can dynamically change how the schedule, the policy of the cluster behaves. And in addition to that, we also present reinforcement learning algorithms that can bound the co-scheduling decisions that we will be making. And okay, so this ASAX is basically also an architecture for co-scheduling jobs in HPC, and it transparently abstracts the resource management from applications because it runs on top of Mesos. It already offers fault tolerance, resource isolation and control, and elasticity to applications. Yeah, so, and then this architecture also allows us to propose new scheduling algorithms, because it's I mean, every schedule decision that needs to be made, it's sent to the algorithm, and the algorithm takes, and new algorithms can be tested and evaluated. And yeah, so I will present this algorithm here now. It's lots of things here, but basically we have a queue job that we want to schedule as quick as possible. And for that, first we need to have an allocation that satisfies this queue job requirements, the constraints of like how many resources or for how long that job wants to run. This is handled by Mesos. Then we have also the actions in the reinforcement learning framework that I just discussed. And in here, for us, the actions are C group quota controllers, like how much quota to the co-scheduled job it will receive. So if, for example, here we have 10 actions. The first A0 would be 0% quota, the second 10%, and the last like 90%. 0% here represents you don't co-schedule, and 90% would represent yes, co-schedule and even give a lot of resource to that co-schedule job. So, and then we initiate here in line 2, like some of the losses for our actions. And then we use this decision trees that will influence, that I will explain a little bit, to influence the co-schedule decision that is being aggregated. And yeah, so you can use as many decision trees as you want, because decision trees are very easy to be evaluated. It's yeah, it's a logarithm in the processing, so it's very quick. And then in line 7, after you evaluate all these decision trees, you create your co-schedule probability distribution, and then you sample an action based on how this probability distribution is built. Then you collocate the job there, and then you evaluate the loss. And the loss for us is it's in relation to the requested runtime that the user asked for. So, for example, if the user asked for like 1 hour, and the job, the 2 jobs that were collocated run in less than that, then the loss would be 0 because there were no loss. But if jobs run is lower, then the loss is calculated in proportion to that. Okay, and while like the algorithm also adapts when too many bad decisions are being made, this green rectangle. So this while basically checks if it can, we just use the default value of 1, but it could be anything. If you want to be more aggressive, you go lower than 0. If you want to be more relaxed on your co-schedule decision mistakes, you go higher. So it then, if it checks too many losses, it accumulates too much losses, then it resets the algorithm so it can be adapted to changes in the collocations. Okay, so the also something that we are using in this decision trees are metrics that we call the happiness metric. So basically, scientific workflows, you can have a certain number of tasks that it has to complete to finish the execution. And this metric basically is something that if it's around, if it results in 1, then it means that the throughput or the tasks that are being completed throughout time are good. And if it's above 1, it's very good. And if it's under than 1, it means it's very bad. So all decisions trees that we use to influence the co-scheduling decision are based on that, on this metric. And just an additional explanation for the decision trees, they can also represent the human in the loop addition that we wanted to have in the scheduling decisions in HPC. For example, because the user, when they are developing the applications, they know most about, they use debuggers or they use tools to optimize the code, so they know a lot about the application. So they can represent using decision trees. For example, if for example, you have, like, let's say the decision tree is saying that the CPU utilization is high. What would happen if we co-schedule an application that also uses high CPU utilization? So the user can represent that knowledge directly into a decision tree, and this would influence how the scheduler would take decisions to co-schedule additional application. So, okay. Okay, so then we are, for evaluating this algorithm, this architecture and everything, we have our cluster here at the university. It's a NUMA scale system. It's basically a system that shows to the operating system multiple nodes as a single system. So here we have 6 nodes, 24 cores, AMD Opteron, 185 gigabytes of memory. So this is basically one single system with 280 cores, 1 terabyte of memory that the hardware presents to the operating system. We use Slurm with default backfilling. For workflows, Montage, another workflow, mostly I/O intensive. Blast, bioinformatics codes, mostly CPU intensive. The statistic is network intensive because it exchanges some messages among the tasks of the workflow, and the synthetic workflow that we did ourselves that is very CPU and memory intensive. the strategy that we are comparing are three. The basic is learn scheduling with backfilling. Also a static configuration where mostly two jobs are co-located where each gets 50% of CPU quotas, and ASAX, the third strategy for scheduling jobs. We submitted in total 45 jobs with varying resource geometries, varying from 1 core to 64 cores. And 3 cluster size, 64, 128, and 256 cores. The metrics that we collected, total runtime, response time, and waiting time. The metrics or sensors that we use to represent the state through the decision trees that I explained are CPU utilization, memory utilization, the type of the job, if it's parallel, meaning it's using all the cores, or sequential, using just one core, the time interval where we are taking the co-scheduling decision, which means we get the requested time that the user wants to run that job. We divide in 10 interval, and then it represents which interval it's in the execution, and the happiness metric. So here, the results for MAKESPAN, we can see that ASAX, because it's co-locating, it ran, let's say it finished the 45 jobs workload faster than the default is learned. And the static configuration, because it's not really smart just splitting the CPU, it's always taking bad decisions. And you can see here that ASAX, it basically co-located jobs that are with, let's say, complementary resource needs. So for example, Montage, which is IO intensive, and Blast, which is CPU intensive, can easily be put together, and they don't influence that much in the execution of each other. And this goes even when we have different cluster size, as we can see with the green and the blue curves. For average workflow runtime, this figure is can be a bit too much information, but it's basically showing that the same run for the same applications, but they are using different amount of resource. So if one application is very scalable, it means that more cores you give to it, the faster it will run. And because of that, also the larger will be the standard deviation that we show here. When the application is not scalable, it doesn't matter if you give more resource to the application, it will not run too much faster. So we can see here more or less that Montage and the statistics, they are you give more resource to them, and doesn't matter, they don't execute faster. But Blast, on the other hand, and Static, they have very high standard deviation because of that. And then this third result with relation to response time, we have, and also we show the CPU utilization waiting time here, which very important. We reduce quite a lot in relation to Slurm the waiting time. It's reduced like in 0.3 hour, and also the response time to complete the workload. So yeah. Okay, so in conclusion, we are basically showing some adaptive and smart co-scheduling algorithm with some very low slowdowns for the majority of workloads. We agreed that we could definitely we should try more diverse set of workloads, and also different jobs arrival, different everything to improve probably the way we are presenting things. But yeah, it worked very well, and 20% improvement in the response time over Islam. It's something that it's representative. Even when the cluster had high loads, it improved the response times. As a future work, we should probably analyze how adding new decision trees for co-scheduling decisions at runtime, how the argument will behave when we do such a thing, because mathematically speaking, this would change the way the optimization that is being done by the algorithm works. So I don't really know how this would behave, but it's something that we can analyze. And yeah, that's it. Also, the happiness metric also seems to capture very well the behavior of an application that can be when you can represent the amount of work that it can complete and tasks per second and throughput and metrics like that. And yeah, okay. Thank you.
Thank you very much. So we have, let's say, 3 to 5 minutes for questions and some echo. Do we have some questions? Well, I would like to know, because I missed that, I'm sorry. Is this a simulation or actual system running?
No, it's an actual run in our internal cluster. Yep.
Good. I like that. Yeah. So it's fully working and
lot of debugging.
So I think then that your PhD is well deserved. Congratulations.
Thanks.
Hi, I have a quick question here. So you mentioned you actually run it on your real system, and so how? I mean, are you talking about the inference part, or talking about the training part? And if it's training part, how long it takes to train a reinforcement learning model on a real system?
So in reinforcement learning, you don't really train anything. You act in the environment and you collect the reward, and that's how you learn it at runtime, dynamically at runtime. So
Okay.
there is no.
So how long it takes to converge to a more stable stage?
Yeah. I mean, of course, when you have lots of actions to be taken, then it converges more quickly. But the thing is, in this case, the problem is when the workload, when new jobs come in, how the convergence, let's say, will be affected. And because of that, we have this green part here. Because in normal reinforcement learning, this is also a new thing, because it's adaptive reinforcement learning. So the curve conversions, let's call it, it's adaptive. So because if you converge in the reinforcement learning, then you learn everything, but that's not really the case, because new jobs can pop up and then adaptations are needed. Yeah.
Okay, I see. So by saying adaptive learning, you mean you actually change the converge goal, gradually when you have new workloads coming in.
Exactly. And
so it's always running in the future. When the class is running, the agent is always running there.
Exactly, yeah. Every scheduling decision is going through this algorithm, and it checks the loss. If accumulated loss are too much, it adapts the algorithm. So it's like a new convergence curve needs to be built.
Okay. Okay, that's okay. Great. I just thinking there's still gonna be like a delay. You're trying to catch up with as a workload changing, right? I mean, how effective?
There will be a delay because you need to learn again, right? So, but you don't lose the learning that you had previously on your bad choices, let's say, because the probability distribution is just rebalanced to converge to the new optimization that we need to do.
Cool. Great, very interesting. Thank you for your answer.
Thank you.
Okay. If you don't have other question, we have perfect timing, and I would like to welcome Marta Jaros here with us. She's good, and her paper will deal with performance and cost optimization for moldable scientific workflows. So, Marta, the floor is yours.
Thank you. Hopefully you should now see my screen.
Yes.
Great. Okay, so hello again. My name is Marta Jaros, and I'm a PhD student at the Brno University of Technology in the Czech Republic. And my today's presentation is about performance cost optimization of moldable scientific workflows. Scientific workflows may contain a big number of various tasks of different nature. Such a workflow can be described as a task graph, as you can see here on this slide. And its nodes represent tasks together with the execution instructions. By execution instructions, I mean workload time, number of nodes or threads, selection of hardware, and so on. And edges represent task dependencies. Moldable task means that we can change the task shape by changing the execution parameters. You can imagine it like a Play-Doh. And why do we want to change the shape of the task? It's because by changing the shape of the task, we can change the final mapping of task onto resources. Here I have two examples of schedules of tasks mapping onto computational resources. You can see it here on the slide. And in this case, on the right side, you can see that we achieved a shorter execution time just by slightly changing the execution parameters of this workflow. What is important to say that while changing the task shape, the amount of useful work is constant. However, the efficiency gets worse while adding the number of nodes because of increasing overhead. I try to depict this problem on this picture. Well, in practice, the user selects, or the user has to define the workflow, its structure, together with the task dependencies. And together with this, a user has to select the execution parameters for each task in the workflow individually. The user usually has to know something about the cluster and about the scaling of each task in the workflow. However, doing this is quite tedious even for expert users, and it is quite common that the user's selection is not very suitable, and typically the workload time is overestimated, which causes long waiting times in the computational queues on the cluster and worse cluster utilization. So to this problem, I'm trying to react by developing the genetic algorithm-based application that automatically selects execution parameters and optimizes their selection to meet given constraints, like minimal execution time or minimal cost. To be able to select execution parameters, we have to know the strong scaling for each executed task. The workflow structure is translated to a 1D array where individual elements represent the tasks within the workflow, as you can see in the picture. The genetic algorithm then finds candidate solutions by searching the search space, and the quality of solutions is evaluated by objective function. The output of the genetic algorithm is a proper selection of execution parameters for each task. Those execution parameters are then used at the workflow submission time to improve its submission and hopefully calculation. To implement this application, I used PyGet, an open source Python library for building the genetic algorithm. So I've designed 3 objective functions. I will start with the local optimization. The local optimization selects the execution parameters for each task in the workflow independently. So each task is optimized individually. And the total execution time of the workflow is the only evaluation criterion. On this slide, you can see that colors in schedules correspond to the colors of the task in the workflow. So you can easily imagine it. Next, I designed 2 global optimization functions. Those functions have 2 optimization criteria and a trade-off parameter to give weight to one criterion over another is introduced. The common criterion for both functions is a total execution time, so-called MAKESPAN. The second criterion for the global optimization with on-demand resource allocation is a computational cost. The cost is calculated partially for each task and then summed up. The second criterion for the global optimization with static resource allocation is the amount of used or unused resources. In this case, the computational cost is fixed because we pay for the size of the allocation we accounted for. So the goal in this case is to use the allocated resources as much as possible. Well, so to be able to evaluate the candidate solutions that are found using the genetic algorithm, I've designed and implemented a simple cluster simulator called Tetrisator. The Tetrisator simulates artificial HPC cluster with a predefined number of nodes and omits queuing times for the simplicity, and tasks are submitted to the simulator in the same order as they are defined in the solution encoding. For the experiments, I've created performance datasets that contain real strong scaling data of the K-wave simulation that I obtained on the Czech Barbara cluster. For my paper, I used only the first dataset that is highlighted with the red line. On this picture, you can see that the strong scaling curve is a bit bumpy, but I have to say that this curve is still quite nice. Next, I designed some workflows that I use for experiments. There are two types of tasks in these workflows that alternate. It's a lightweight data processing task and heavy simulation task. These tasks differ in the strong scaling and the maximum number of nodes that could be picked for the execution. On this slide, I picked some results for the kind of workflow that you can see below here, and global workflow optimizations. On both figures, you can see Pareto frontiers together with denominated solutions for different trade-off parameter alpha. Both pictures has the execution time on y-axis, and on x-axis is cost or unused resources, respectively. In this figure, you can see that found solutions form quite nice clusters for different alpha parameter. And these clusters are somehow overlapped on the edges. But the clusters are great. It says that we can prioritize one optimization objective over another. Overlaps are a bit worse, but I think it could be improved by some tuning of the function parameters. What is important to know at this point is that if we want to minimize, for example, the computational cost, then we could get a solution that is cheaper by approximately 10%, and the execution time is by 30% longer. This is the actual space in which we can find and select solutions. The second figure shows the global optimization with static resource allocation, and in this figure you can see that the overlaps are much more bigger. So in this case we didn't manage to use the alpha parameter as expected, and from my point of view in this case the alpha parameter of 0.05 value is the most reasonable one. Here on this slide, I would like to share with you some of the evolved schedules. Since the result could not be directly compared, I just highlighted some main differences. So in the first column now you can see the local optimization, and in the second, or in the middle one, you can see the global optimization on-demand allocation. In case of the local optimization, we minimize just the total execution time. And in the red, you can see the achieved workload. The red arrows in this slide is for you to more easily navigate between numbers on axis. In the case of global optimization, the cost and the execution time are balanced. Here we do not pay for white spaces. You can see that the workflow is reduced in both cases when compared to the local optimization. And on the top picture, we also managed to reduce the computational time by 30%. In the second case, although the MAKESPAN is bigger, we managed to reduce the execution cost by 40%. Now I'm going to compare the global optimization with static allocation to the local optimization. And here, although we weren't able to use the alpha parameter as expected, we finally managed to increase the workload which is great because in this case we pay also for white spaces in the graph. It means that we pay for resources that are not used. And when compared to the local optimization, we've got solutions with shorter makespans in both cases. Well, to conclude this, I can say that we managed to evolve schedules that may prioritize either computational time, cost, or workload using the trade-off parameter that in practice could be implemented as a slider, where you can choose between the minimal cost, minimal execution time, or minimal idling resources and the execution time. Schedules for workflows consisting of 64 tasks could be evolved usually within 2 minutes, at maximum within 5 minutes, but it's still reasonable time for us. Now I would like to say a few ideas that are to be addressed soon. First, I would like to tune the fitness function to better how to say that? You can see it on this picture that there are high overlaps. So I would like to tune the fitness function parameters to get nice clusters as in the previous method. So I could prioritize unused resources and elapsed time. Next, I want to study and implement some optimization heuristics. Probably those heuristics would be based on the critical path in the graph. Then I would like to validate our approach against standard task graphs, because in this paper I've used only 2 experimental graphs that weren't so big. Next, due to inability to hold all possible performance input parameters, interpolation techniques will be incorporated. I've already made some experiments, so I would like to use it together with the presented approach today. And finally, I would like to upgrade the functionality of Datacenter, since we use PBS-based clusters mainly, and they use backfilling methods. Or I would incorporate some already existing cluster, for example, ALEA cluster simulator, which I also tested in history, and I think it's a quite nice tool and robust. Finally, I would like to integrate a mechanism that gives some feedback about actual cluster utilization, because at this time, all approach stands only on historically or on performance data that were collected in history. So that's everything from my side. If you have any questions, I'll be happy to answer them, and thank you for the attention.
Thank you, Marta. I'm sorry. Do we have some questions? I missed the part about the alpha parameter. The alpha parameter is related to the genetic algorithm, or is something?
No, it's not related to the genetic algorithm. It's a trade-off parameter that is used in global optimization methods, and it enables you to prioritize one objection over another.
Okay, okay.
So it's
So it's it's basically a weight in
yeah,
those
yeah,
two sub-criteria.
right.
Yeah. I think you should look into the related work, because this seems like something that is quite, it has been studied in the past, I think, but I wasn't involved in workflow scheduling during my studies, so I'm not an expert. But I was playing, let's say, with meta heuristics, and what I found during my studies was that besides, let's say, genetic algorithms or simulated annealing, surprisingly powerful was, what was the name? Let's say random search or Monte Carlo approach, where the trade-off there is that you simplify the method, but you achieve higher speed. So when you compare the runtimes, I always achieved better results using, randomized method, let's say, that didn't use some, this fancy stuff like mutations and crossing of genes, and I don't want to say that it's a good idea, but my experience was that in my case, which was simpler case, it was a good idea to try a simple but faster method.
Okay.
Anyone else?
So I had a question. In like looking at the static on-demand approaches, they rely still on moldable approaches, right? In which you choose the size of every stage when you started.
Yeah.
In high-performance computing or dependent system, it gets complicated when you try to do dynamic resources. But what is your take on malleable stages like that? So have some kind of feedback loop that as the stage is executing, you can actually reshape it, and not every workflow supports it, right? But what is your take? I mean, what do you see are the benefits you could get from doing dynamic allocation during the execution of a stage of the workflow?
I'm not sure if I understand. Could you repeat it?
So in the approach, if I understood correctly, the on-demand approach calculates the size of the job that you need, or the amount of resources that you need to run every stage at the stage execution moment, right? It does, but it doesn't change once the stage starts. It doesn't change the amount of resources, or does it?
Well,
like for example,
yeah, continue.
No, like for example, if you in the middle of the stage you could realize that when your estimation of resources is not fast enough to complete the stage within a certain amount of time, right? And then on demand you could say, okay, give me more on demand, but like dynamic, you could get more resources. Does your approach do that, or your approach is just calculating the stage size depending on where you're in the workflow?
I select these parameters for the whole workflow at the beginning, at the submit time.
Yeah.
But if anything changes on the cluster that I realize that it's not suitable or not good for me, I can possibly reschedule the workflow or some tasks of the workflow.
I see. Okay. Okay, maybe we can follow up offline. I think it will be probably easier in Slack. Okay, thank you.
Thank you too.
If there are no more questions, we have a short break and good timing. So the break was planned for 5 minutes, but because we have 5 minutes left from from the discussion part of this talk. So we can either discuss or have 10-minute break. And I think we deserve it because I need to get some coffee or something.
Yeah, let's go for coffee.
Okay, so if you agree, let's meet in 10 minutes with the last session.
Yeah, +1 for coffee.
Okay, guys. So see you in 10 minutes.